So here I'm going to do another limit of a sequence, and we're just going to do it. Just involves a little bit more of an advanced technique to find the limit. So here we have is the sequence n plus ln of n all over n squared for defined for n greater than or equal to 1. So we want to find the limit of this sequence. Now the first thing is recall that there's only one type of limit of any sequence, which is the limit as n approaches infinity. So we're going to write out the limit as n approaches infinity of n plus ln of n over n squared. Now, as we said in the last example, technically what I'm supposed to do is I'm supposed to leverage what I know about functions f of x. I'm supposed to redefine this as a function of f of x and calculate the limit that way. The important thing to recognize here is that I could do this. All of these terms are defined for all real numbers x greater than or equal to 1. So I'll simply note that I could change the variable to the real valued variable x, but I'm not going to do that. I'm just going to treat this as if n is a real valued limit, and it is a real valued variable, and I'm just going to continue to use the variable n. So here, first of all, let's use some of the limit rules that we know. This is equal to the limit as n approaches infinity of n over n squared plus ln n over n squared. And of course that's going to equal limit as n approaches infinity of 1 over n plus ln n over n squared. Now, we can easily see is that this limit approaches 0. In other words, as n grows to infinity, 1 over n is just 1 over infinity, and that's going to be 0. This limit here, on the other hand, the natural log function grows to infinity, and so does n squared. So what we have here is an infinity over infinity type limit. So using the laws of limits, this is going to be limit as n approaches infinity of 1 over n plus the limit as n approaches infinity of ln n over n squared. Since this is just equal to 0, that's going to be 0 plus the limit as n approaches infinity of ln n over n squared. So coming all the way back here, 0 plus this limit is just going to be that limit, so I can get rid of that 0 right away. The infinity over infinity limit I'm going to evaluate by L'Hopital's rule, and I know it's sort of a convention many of you learned that when you're actually using L'Hopital's rule, you want to write over the equal sign, you want to indicate that you are. I know that some people will just write like an H. Some teachers say to write an H for because it's the L just means the in French, so they begin it with H. The fact is that I don't like abbreviations, although I've never been too big on this notation at all, or requiring its use. I do like to write it in kind of a fastidious way, so I actually write it with the lowercase l, apostrophe h, accent circumflex, and a p, just like that. And that's really fun when you type it, when you have to type it like that. So anyway, this is using L'Hopital's rule. We can declare that the limit of this infinity over infinity type function is equal to the limit of the derivative of the top over the derivative of the bottom. Recall L'Hopital's rule. It looks like the quotient rule for derivatives. We're not applying the quotient rule for derivatives. We're separately taking the simple derivative of the top over the simple derivative of the bottom. The derivative of the natural log function is 1 over n, if it's the natural log of n. The derivative of n squared is 2n. So this is equal to the limit as n approaches infinity of 1 over 2n squared, which of course equals 1 over infinity, which is 0. So this is a little bit of a refresher on L'Hopital's rule, and also just a demonstration of the fact that the same rules that you know for finding limits of functions apply for finding limits of sequences.